Hi there, and a very warm welcome to this week's video in which we are going to continue to look at lasers. So last week we looked at light projections and therefore make our lasers, and this week we are going to look at a completely different scenario, a completely different setup in which we are going to use OSL but other tools as well. So without further ado, let's grab your coffee and let's make some lasers. Let's have a look what we're going to do today. So if we zoom out, you can see we have a null here. And when we move the null, you can see those lasers are forming on those bolts. Now, this scene isn't very complicated other than the OSL script maybe. So let's build this from scratch. Alrighty, let's create our scene. This should be rather fast. Let's create a cloner object, and in the cloner let's set it to grid and set the count in the y-axis to 1. Then, while the cloner is still active, create a sphere by holding down shift to make it a child, and go with the radius 50 and the segments 64 to make it a little bit more smooth. The way our laser will be working is with intersections, so we need an intersection plane or intersection geometry. And you need to make it as large as the scene, or at least as large as you think the laser should reach. Next, we need to add an origin point for our laser, so let's create a null and call it laser. Here we go. And then to actually make the intersection follow the laser, we need to go to animation tags on the plane and add a target, and this obviously would be the laser. So if we move not the plane, if we move the laser around, you can see now the plane is following it. So in order to see something, we need to add a light source and materials. Let's do this by going to objects and then texture environment. This will be our visible environment and will be black. So let's call it background. Here we go. Then finally add the light source, so HDRI environment, and you know where this is going. So we bring in the HDRI from Maxim Ross yet again. Let's see if this is working by rendering and call that HDRI. Here we go. To bring this base setup to a close, let's create a glossy material and assign it to the sphere, and then make this material a little bit darker in order to make the laser show up better. And as you know me, let's go with a GGX BRDF and a roughness of 0.5. Welcome to the actual tutorial. First, we want to make our intersection plane invisible. We are going to do that with a material, so let's create a diffuse material and make its color black. So let's go to the diffuse and set it to 0. Then assign the material to the plane, let's also call it plane. And then we are going to use a ray switch here, so ray switch, and assign it to the opacity. And then we're going to set every value to 0 but the ambient occlusion ray. Here we go. Like this. And exactly this should leave a huge clue what we're going to do next. We could build our laser setup directly in the bolts material, but to be more flexible and assign it to other materials as well, we're going to opt for yet another shader. So let's create a diffuse material yet again, and then go from there. As you probably expected, we are going to make a dirt node here and then plug it into the opacity and then assign the material to the sphere, and we can already see what's happening here. Let's make this a little bit more pronounced by going with 1.5 and a strength of 5. And then also, this is just one side of the dirt from the plane. Let's duplicate the dirt node and invert the normal and then multiply them together. Obviously, this needs to be inverted because right now everything would be laser, but the small sliver here that is showing the original material. So let's do this and go with an invert. I already set this up before. So here we go. And now we have our laser showing up at the right portion. Now, obviously, lasers are not made up of diffuse materials. So let's change that by going to diffuse and set this to 0. And then go to emission and create a texture emission here. This texture emission is very bright, so what we need to do is get this to surface brightness. I explained this one in depth in the laser part 1 tutorial. It's linked in the upper right corner if you're interested, and then go with a brightness of 10. We can adjust that later on if we're not satisfied. And then, last but not least for the section, let's give it its red iconic laser color by going with a RGB spectrum and then making it red. And this is also explained in the last tutorial. I'm not going with a full red color because that can lead to problems in the rendering later on. Alright, cool. So we have our laser now, and if I move our laser null, you can see it's following nicely, but it lacks the direction. And this is where our OSL script comes in. Alrighty, let's think through what we need to make this direction-based laser setup working. Through our null, we already have a point in space where the laser is originated. So what we need to do is compare this point in space with the surface normal of the objects, and then where it aligns, where it's parallel, have the brightest point, and where it's 90-degree offset, have it sort of fade to black. Fortunately, we have a setup like this in mathematics, and we already touched on that in the Octane Better Falloff shader tutorial. Again, link in the upper right corner. And what I'm talking about is the dot product. It has been ages, so I'm really happy to welcome you to another ChartTime. So with a dot product, what we need to get is the vector for our null object, so the direction in space where the null object is oriented, and then the normals of our surface. And when they are 90-degree offset, our value is 0. And the more we align them to each other, the higher the dot product is getting, and when they're totally in parallel, the dot product is 1. And as said before, this is exactly what we need. So let's go back to our scene and implement that in OSL. I hope you're hyped for some scripting action, because that's what we are going to do now. So if you haven't worked with OSL scripts before, the easiest way to get going is to search for OSL and then add the add OSL, because this is really easy to understand and we can work from there. Let's plug this shader into the opacity instead, and then open the editor and make it a part of the layout, for example in this column here. Let's have a look at the add shader script, so you can hopefully realize that scripting OSL is not that hard at all. First of all, we start out with a line that names the shader, and then we add our inputs and outputs. So we have two color inputs called A and B, and those are reflected here. And then we have an output called C, and this is this one here. And once those are added, we have something to work with. So basically, this is all the formula we need to get an add shader. We say C, which is the output, equals A plus B. So we just add A and B together. Of course, this is probably the most simple OSL script there is, but it's very nice to understand the whole function of it. So let's start conforming this script to our needs. When I started to think about this first, the problem was that I didn't know how to bring in 3D data into the shader, because this is right now living in the shader land and our null is living in the 3D land. But then I remembered from our fields tutorial a couple of videos back that Octane allows you to link objects to a shader projection. So the first thing here we are going to do is to change up the color that's an input into a projection input. So right now the data type for port A is set as color, so that means you can plug in color data. In order to make Octane use a projection, we need to change it to point, and then also set the variable to something accordingly. For example, XYZ. Here we go. Now, obviously that throws an error because we are not using the variable A anymore, but let's keep on editing. We also don't need the color B, so let's just delete that. To make you see something, we are going to switch the opacity to the diffuse for a second, and then type in the value N here, and N stands for normal, and this is a standard library function. So if we do that, we can see the normals are showing up on the balls. With our latest action, you might have noticed that our node doesn't have ports anymore, and one of those ports moved into the coding area here. But since we really want to connect a projection node, we need to tell the OSL script to put that out as an output. Let's go back into our script and tell OSL exactly that we need UVs to come in here. So what we need to do is go with a point again, and then a parentheses, and then tell it what data it needs to receive, U, V, 0. Here we go, and if we compile now, we get our port that we need. So let's do what we actually came here to do, use a projection, and then pipe it in here. So if you would do something wrong, this connection wouldn't establish. So if you are able to connect it, congratulations, you made yourself a projection. Last but not least, what we need for the projection is the same that we use every time, XYZ to UVW, and then actually go into our objects and link the laser in here. Same as in the fields video, to make it work correctly, we also needed to set to world space instead of object space. So now that we have every data available that we need to get our dot product going, let's get our dot product going. First of all, let's make our OSL script active again and then make another line here and then declare a float. Let's name the variable dot with a capital D and then equals, then dot without a capital D and then a parentheses again, since the small dot is our standard library function for a dot product. So inside of the parentheses, we need to bring in both vectors. So the n vector, then separated by a comma, the other vector, which comes in through our projection. Here we go. And last but not least, add a semicolon, otherwise the whole formula will not work. To see what we're doing here, let's get rid of the emission for a second and then exchange the n with the dot product here, or the variable. So here we go, and then compile. And we can see it's working, sort of. I say sort of because if you remember, our null object here is on the other side, so something is amiss. So we create shadows where there should be light basically, and this is an easy fix. So the fix is to invert the object vector that comes in with the projection, because right now it goes out from the object to the world and we need it from the world going towards the object. So the easy fix here is going back to our OSL script and inverting that vector here. So what we can do is get another set of parentheses in here. And if you know a little bit of math, you multiply something with -1 to invert it. So if we compile now, then we get the right behavior. And now we get the light coming from the null object here. Alrighty, now that we have all the elements, let's bring everything together in the shader. So what we need to do is multiply our laser shader part and the direction together to get the direction of the laser. Here we go. Obviously, we don't need that in the diffuse, we need that in opacity, and then also add the emission. Here we go, we have our laser. Two things that are rather important. So one, if we just move the null, you can see we have an update issue somehow. To mitigate that, we can give it a Octane object tag. So go to extensions and then object tag and then go for force updates enabled. And you can see now it is moving accordingly. But only do that on objects where you really need it. And second, concerning the dirt maps, since those are live dirt maps and therefore the laser would show up at edges of the original object, now we have a sphere without edges so it doesn't show up, we need to actually set this to the include object mode to others. And I guess this brings us to the limitations of this method. So for example, there's no shadowing. With the light projection method, the spheres in front would shadow the spheres behind. But since this is just a direction-based effect, there's no notion of shadows in the shader. Another limitation I spoke of a second ago is that you cannot restrict the dirt to a single object, so if we bring in another plane, then the laser will show up there as well. I really wish Octane had the feature to restrict its dirt to one or a set of objects. With that current insufficiency, it really depends on your scene, dependent for example on the amount of intersections. So I recognize this channel wouldn't be this channel without some bonuses. So what I added into my shader was also a gamma function to control the fall off of the light here. This is a 3-step alteration process to our formula, but it's rather easy. First of all, we add another input by adding a color and then gamma and then equals 0, comma. What I actually haven't mentioned before is that half of our formula hides behind negative values, so we need to clamp those first before we go into the power function to get the right gamma. To add the clamp function, we add yet another line here and go with a float again, so I'm stealing that from above and calling it clamp dot. Here we go, equals, and then we go with another library function, which is clamp. Then the parentheses as we had before. Then what we want to do is bring in the dot. So the first value in here is the actual value. And then we decide where we want to clamp it. So 0, 1. We clamp it from 0 to 1. And to round things off, we end up with a semicolon. And the third step in our 3-step process is actually the power function. So let's do this and write this in here. So instead of getting the dot to the output, let's declare a color once more, then again parentheses, and then go with the power function. This is POW. The power function has a parentheses on its own, so we need to declare those. And then inside of here, we are going with the clamped dot, and then go with a comma, and then we declare the gamma that comes into the another input of our shader. Here we go. As you might have noticed, during we scripted around here, there's the other port that turned up in the OSL texture, and something impossible also happened here, since the projection is not allowed to go into the gamma. So if we unconnect it and try to reconnect it, this is not allowed anymore. So what we want to do here is make this a little bit bigger and then go for a float texture to get into the gamma. Here we go. With that, you can adjust the emphasis of the fall off here, so values below 1 emphasize the back of the curve, while values above 1 emphasize the front of the curve, so you have more of a gradient here, especially if you go with very high numbers. And not sure if that's visible in the recording, but I have a small line where the intersection is happening. If you want to get rid of that, you have to go to your ray epsilon and add a 0 here. So this makes the precision of the calculation higher. Okay, spontaneous and unplanned bonus 2. This ironically might be the most revolutionary one. So kudos to you for hanging on. You can have this gem as a reward. So while editing this video, I was thinking about, do we need a plane at all? Can't we just do all of this with fields? And yes, it's actually possible. So we can move around the null, and it is updating with fields now instead of an intersecting plane. All I needed was a virtual plane, so a null object that still gives me the angle for the real plane. And then I was going with this gem here, the planar projection, that created a virtual plane in my shader. And then I thought, why stop here? Why not also add a fall off? So we can actually set this to a lower value. And if we move the null closer, you can see that the further away from the null, the dimmer it gets. So a real fall off. So if you watch the fields tutorial and also watch this tutorial, you have the full power in your hand to create the best laser shader there is. If you don't want to build it from scratch and get it as is, then you can subscribe to my Patreon. The lowest tier will do, and you get your hands on both of those shaders, the ambient occlusion one as well as the fields one. And this brings us to the end of this tutorial. As always, let's thank those who made this video possible. Obviously, my Patreons. Especially my €50 tier subscribers, Shields Augustinen, Just a Freakin', and Leon Studio TV. Also, of course, a huge thank you for my €15 tier subscribers, for Die Thieves, Render King, Alessandro Bonchio, Alessio De Vecchi, Alihan Gekkefa, BVR, Chris Fritchie, Christian Grajewski, DBMD, Erbe Plus Akademie, George Luna, Graham Bucknell, Harish Pavaskar, Joel Mackimer, John Edward, Ludger, Muradan Axos, Nico Straub, Part 1 of 2, Kuok An Dang, Random Capybara, Raiko, Renato Marquez, Reshock, Shiro 2049, Terry Wayne Ranson, and Yassin Rupp. Welcome to the Fields-Driven Laser Show. Thank you very much for sticking with me that long. This again was one of those tutorials which went longer than expected, so it's a joy to seeing you here at the very end. If you want to show your support, let's post a brighter button in the comments down below. Other than that, I wish you a great rest of the weekend, a fantastic start into this week, and a lot of fun on the central finite curve of shader creation. That leaves me with my final words. Ist immer noch Laser, wie du abgehst. Bye.